like to go straight into our next speaker, Angappan. So Regu did his PhD in planetary science at Johns Hopkins, where he still holds a visiting scientist position. But he's a postdoctoral scientist at SandboxAQ, and I'm very excited to see how he's going to show how AI and quantum physics can combine to help us navigate the world. Thank you, Regu.
Thank you, organizers. Thanks, Michelle, for the introduction. Before I get started with my talk, I wanted to introduce myself so that you understand where I'm coming from on what I'm talking about. And I'm a postdoctoral scientist, so I'm always looking for new collaborations, new opportunities, new mentors, and new mentees. So if any of this resonates with you, please do reach out. So I'm a planetary physicist by training. I'm also an educator, and my research interests are in fluid dynamics, magnetohydrodynamics, mathematical modeling, things like that. But I'm also interested in pedagogical approaches, science education, arts and science, and what I like to call be a Jedi, giving a sense of belonging in the sciences, making it accessible, just, equitable, diverse, and inclusive. And I do all of this applying a modus operandi of empathy, creativity, novel and conventional approaches, and hopefully you'll see a little bit of that in the talk that's to come. So back to our topic. It said, understanding and navigating our magnetic world with AQ. What is AQ? It is the combination, it's a powerful combination, a union of artificial intelligence and quantum physics-based innovation. So it combines the power of both. That's what AQ stands for. Why AQ? What's so special about it? So the quantum physics aspect gives us the accurate and sensitive observations, and AI brings efficient and effective data processing to those observations. So that's the idea behind AQ. And that's what SandboxAQ does. SandboxAQ, we focus on 4 main AQ solutions. So we have cybersecurity, so quantum cryptography, AI and quantum sensing, which I'll talk more about, and AI simulation, so doing quantum calculations and computings to determine new material, drug discovery, and so on. We'll focus on AI and quantum sensing today. So why quantum sensors? What does quantum sensing enable? Quantum sensors beat current limits. There's no drift in quantum sensors over time. And they're much more accurate. And so they're very precise devices to measure various things, and today I'll be talking about magnetic field sensors in particular. Now you combine all that very sensitive observation with the power of AI to be able to tease out different signals, and you can make some really cool discoveries. At SandboxAQ specifically, we use magnetic quantum sensors for 2 different things. So there's biomagnetic sensing. You've all probably heard of echocardiograms. There's a magnetocardiogram, which can detect electrical signals from the heart in the neurons, and non-invasively be able to tell you when something is starting to go wrong. And there's geophysical sensing, so you sense the magnetic fields from the Earth system, which I'll talk a lot more about today. That's my focus. So I wanted to give everyone an overview of our magnetic world and what is it that these sensors are picking up. Oh, there was supposed to be a movie here. I'm not sure if the movie is going to play. But if you saw the movie, we'll just go on to the next slide. The magnetic field of the Earth is predominantly generated in Earth's core, in the liquid outer core. So the mechanical motion, the churning of a liquid iron ocean 3,000 kilometers beneath our feet, that mechanical energy is turned into magnetic energy in a dynamo process that creates the magnetic field of the Earth that we can detect with compasses. We call the North Pole, South Pole. But it's not just that. Rocks that form in that magnetic field retain a component of that magnetic field when they lock that in as they're forming or as they get set. And that is a different signature because these rocks are forming over time and the magnetic field is changing over time. So there are two components already. But we really like this component in particular because you're not just able to navigate between north and south, but it's almost like you have a fingerprint. So if you know where you are on this map, you can use this magnetic field signature to get around and navigate the world with. So it's a new form of map. So we really like this field. But that's not the only magnetic field either. You see a picture of a solar flare. So the solar wind carries magnetic field from the sun. That magnetic field interacts with Earth's magnetic field. When two magnetic fields interact, they create current systems, and those current systems in turn create more magnetic fields. So it's starting to get very complex. And I'll walk through some of these different current systems that are dominant. So you have the magnetopause currents. That's what we call the magnetosphere. Magnetotail currents, and Birkeland currents. Birkeland currents are very interesting because that is where open energetic particles go along the magnetic field lines of the Earth, and they interact with the atmosphere to cause auroras. And there is a ring current system, but we're not quite done yet. This is a closed loop, so the Birkeland currents and the ring currents have to connect somehow, and they connect in our ionosphere through a number of different current systems. Now, why did I put this slide up and talk you through all these different current systems? All these current systems create magnetic field. So if we're sensing magnetic field around Earth, we are picking up all of this, and on top of that, any electrical currents that we produce in our system itself, we're sensitive to that as well. So it's a problem of superposed signals that are time varying. This is going to be another strand, perhaps, of talks that are to come. And the scale of it all. So the crustal field that I said is a good map that we can navigate by is about 300 nanoteslas, whereas the Earth's core field, that's the dynamo that's producing the main magnetic field of the Earth, is 5×10⁴ nanoteslas. And all in all here, we have 12 orders of magnitude covered from the human heart, which produces a signal of 0.05 nanoteslas, all the way to an MRI machine. And so if you have a sensor that is sensitive enough to pick all magnetic field signals, it's picking up all of this. So why do we need an alternative navigation technique that's based on Earth's magnetic field? GPS is what we tend to use nowadays, but GPS is not foolproof. It can be jammed, it can be spoofed, and in current geopolitical conditions, it happens quite a lot. So if you are flying and your true location is along that line, and GPS goes out, currently we depend on inertial systems, INS, and that tends to drift over time. So over a certain time period, you'll find yourself quite off from where your true location is. But with this magnetic navigation capacity, we can anchor that drift. So it's not necessarily only to function independently of GPS and inertial navigation systems, but it is also to anchor and give a truth value. And you can't jam or spoof these signals. So, and it can't be changed by atmospheric conditions. So it's unjammable, but we also want to produce a diversity of sensors so that we can navigate robustly and effectively and safely. So wanted to give you a quick rundown of different types of quantum magnetometers. And their main advantage, as I said, is it's long-term stable. They're passive sensors, so they're jam resistant. And what we really like is the sensitivity. It's picking up the whole breadth, that full scale. So how do we process all that signal then? If we're picking up everything, what do we use to process it? And that's where AI and ML come in. So to demonstrate that, I wanted to start off with MagNav challenge. So the US Air Force and MIT did a collaboration where they wanted to pursue this specific challenge, to be able to remove all that is noise and just find the magnetic signal to navigate with. And they flew a Cessna flight, 1 hour flight time, 200 kilometers, and they had a number of quantum magnetometers on the flight. It's an open data set. There is a GitHub page. They even have a Julia code available. So anyone who wants to take a gander at this, feel free to. And you can still give in submissions for this, I believe. And they found that they did improve accuracy over INS. And a lot of the efforts that have come in for this use classical machine learning and deep learning. So this is, me and Alexis did not talk about this beforehand. We have very similar slides here. So I won't go into the details of this, but essentially the question is, can we do better than classical machine learning techniques, which used MLPs, multi-layer perceptrons, or deep learning, the LSTMs, long short-term memories? Turns out we can do better, and there's a paper that was led by Favor Nerys, who is a Sandbox resident, intern, and also a PhD student at Stanford. So she looked at liquid time constant networks, which was developed at MIT. How does this work? It uses ODE solvers, it's very high dimension, and it does sequential tasks. The difference between what you saw earlier and this is it models complex time-varying signals. Temporal dependencies are accurately understood and represented. And the way they do that is, or the inspiration for doing this comes from studying worms for the researchers, which is why they have temporal dependencies. And the benefit is it's more generalizable, it's faster, and you can do it potentially in real time, which is what we would need if we're navigating with these signals. So I want you to focus on the two numbers highlighted here. I'm showing RMSE, so you want it to be close to 0 as possible. The error should be low. And the previous models are quoted up there, and the model that does the liquid time constants closed form performs best. And compared to classical models, we see a 58 to 64% reduction in error when we apply this technique. And what does that translate to in terms of magnetic field signals? So if I have a truth field signal that is plotted over there as my flight is going across, and I have a time signal, time series of it, this is what the predicted signal ended up being. So it looks almost similar to the truth signal. So we got very high accuracy with this technique. That was with the MagNav challenge. But we continue to fly our own boxes, and these are some of our partners in that effort. So we have a number of boxes. We're collecting data all over the globe. So can we do even better with all of this data? The short answer is yes. And to know how, you have to stay tuned. I'll be presenting a talk at the American Geophysical Union meeting that goes into a lot more details on this. And there'll be another talk at NeurIPS both in December. Or you can talk to me after this. Future outlooks with AQ. How does AQ transform the science? That is strand one, right? So we're collecting, imagine a world where we're collecting data on all the flights that we all flew in from. Perhaps some of you took trains and other things, but imagine data collection from all of those. As we fly continuously and get this data that is very sensitive, we're going to be able to identify changes that are naturally occurring in the system itself as well. And soon we'll be able to monitor its changing core and external field better than ever before. And there are some precedents to this. So I, for my PhD, did this as my project where I took the Iridium satellite constellation data, 66 commercial satellites, and took the magnetic data that they had to build a magnetic model of the Earth. Our state of the art before then was about 6 months. You can build a snapshot of Earth's magnetic field. We got that down to 2 hours. So I can monitor Earth's field every 2 hours and see changes that's occurring in that. And the change pattern that was dominant, that was fascinating to me, was you could see a global wave pattern move across the planet in 14 months. And it directly tied to a wobble of the Earth. So there are lots of physical insights from that wave that we can then get. We can learn about the core flow dynamics, the flow in the core. You understand the forces. So that's field of force. You understand core magnetic field strength. We know the strength of the magnetic field at the surface, but we don't know the strength of the magnetic field inside the planet. There's a component of the field that doesn't come up. So we can guesstimate that. And we start understanding the different excitation modes for these types of waves that we observe. And it's almost like an MRI machine. You have the field inside, and we have sensors on the outside, and we get to scan everything in between. So if we can do all of that with just 66 satellites and a grad student, imagine what we can do with all the flights and AI. We can also do better in characterizing external fields. So we know that solar storms happen, and we need to be resilient to that. There's supposed to be a movie there showing Mercury being blasted by external field. So we were able to take messenger data, find residuals in that data, and simulate that. And messenger was not at the planet for very long. So imagine what we can do with a lot more data. So here are some potential possibilities to come. We would be able to predict changes to Earth's core field, which is of interest to a lot of folks. We will be able to predict external field changes and when solar storms might occur. We will answer open questions in fluid dynamics and magnetohydrodynamics. And we'll close the gap in understanding whether you need planetary magnetic fields for habitability and life. So I've tried my best to tie my talk to all the other strands, and I've labeled them here. But all of this wasn't done by just me, so I wanted to give a shout out to the whole team at AQNav. And here are some QR codes for the different references that I shared. So if anyone wants to take a picture, you can of this. And thank you. And to students in the audience, do check out our residency programs. It's a fabulous opportunity. Thank you.